Good morning, everyone. Today's lecture we will deal with the first category of carbonyl compounds, which are the aldehydes and ketones. What are aldehydes and ketones? Aldehydes and ketones are compounds that contain a carbonyl group, but this description applies to other classes other than the aldehydes and ketones. Compounds that contain a carbonyl group can be classified into aldehydes, ketones, acids, carboxylic acids, and acid derivatives. How are they different from each other? In case of aldehydes, the carbonyl group has to be attached to a hydrogen from one side, and on the other side either a hydrogen or another carbon of a regular alkane. In case of ketones, the carbonyl group has to be attached from both sides to an alkane chain. In case of acids, the carbonyl group has to be attached to an OH from one side and whatever groups from the other side. And in case of acid derivatives, the carbonyl group is attached to a certain substituent, whether halogen, whether another acid molecule, whether an alcoholic group or an amine. These are the things that can be attached to the carbonyl in case of acid derivatives. In this lecture and for another two videos, we will deal with the aldehydes and ketones, their general structure, their nomenclature, synthesis, physical characters, and their chemical reactions. The following videos will deal with acids and acid derivatives. Regarding aldehydes and ketones, first of all, we have to look at the carbonyl group. In case of aldehydes and ketones, you have a carbonyl group attached to either a hydrogen or to a carbon. The carbonyl group has an oxygen which is more electronegative than the carbon, and accordingly it attracts electrons, thus it's carrying a partial negative, and the carbon of the carbonyl is carrying a partial positive. And accordingly it's easily attacked by nucleophiles, breaking one of the double bonds between the carbon and the oxygen, breaking the pi bond between the carbon and the oxygen. In case of aldehydes and ketones, the reaction stops at this step. However, in case of acids and acid derivatives, there is a continuation where the double bond reforms, throwing away or giving away a leaving group like the hydroxyl group or the derivative port. Let's now deal with the aldehydes and ketones. As we said, they can be attacked by nucleophile, and this is regarding as nucleophilic addition reactions. Okay, let's look at their nomenclature. In case of nomenclature of first aldehydes, we have the common names as we're used to, and we have the EU pack names. In case of not common names, they will just be memorized, things like the acetaldehyde, formaldehyde. These are just common names that has no origin and has no rule. It has an origin, but it has no rules, so you just memorize them. As for the EU pack nomenclature, you look for the longest chain, the same rule. You look for the longest chain containing the highest priority function group, which is here the aldehydic group. You name it. So for example, here you have 1, 2, 3, 4, 5 carbons. So this is the pentane. And you remove the E and you add an al. In case of alcohols, you remove the E and you added an ol. In case of aldehydes, you add an al. In case of ketones, you add an on. Okay. Regarding the priority, you have the acids at the top and their derivatives, followed by the aldehydes, then ketones, then alcohols. This is the list of priority for what you have studied up till this point. Okay, so this is how we nomenclate them. We look for the longest chain containing the highest priority functional group, which is the aldehydic group. We name it according to the number of carbons present in it, and then we remove the E at the end of the alkane, and we add an al. Then other substituents will be given a number, the least possible number. By the way, you do not have to mention that it's a 1-al. Why is that? Because aldehydes are always terminal. You have the carbonyl attached to a hydrogen at one side always, and then the rest of the chain is on the other side. So aldehydes are always terminal. They come at carbon number 1. Suppose that your aldehyde is not the highest priority functional group. For example, you have an acid on your chain, and then you have an aldehyde as a substituent. In this case, the aldehyde group is considered as a substituent, and it's going to be named 4-myl. So this is the 4-myl substituent. So for example, this is 1, 2, 3, 4, 5. So this is the pentanoic acid. And then on carbon number 1, 2, 3, you have a 4-myl group. This is regarding the nomenclature of aldehydes. As for ketones, again, they have some common names, such as acetone, for example. You have the acetophenone. These are common names for different ketonic compounds. You can use a certain rule for giving common names for ketones, which is that you name the different R groups attached to the ketone. For example, if you have a methyl and a methyl, this is acetone, or you can say that this is the dimethyl ketone. If you have, for example, a methyl from one side and an ethyl from the other side, so this is the ethyl methyl ketone. When you have the name and you're drawing it, you draw the ethyl group, and then you draw the methyl group, and then you put the carbonyl in between. So this is how you nomenclate them in a common way. As for the EUPAC nomenclature, as we have mentioned, you have the chain. You count the number of carbons, 1, 2, 3, 4, 5. So this is the pentane. And then you remove the E and you add an O. So this is the pentanone. But one more thing, you have to mention where the one is. So this is 1, 2, 3, 4, 5. So this is the 2-pentanone or pentane 2-one. You can always place the number before the suffix immediately, or you can place it at the beginning of the name. Finally, if your ketonic group is not the parent, not the highest priority, so it's not regarded as the parent compound. For example, if you have an acid, so this is 1, 2, 3, 4, 5 carbons, so this is the pentanoic acid. And then 1, 2, 3. On carbon number 4, you have an oxo. It's named as an oxo if it's not the parent compound. If it's not the highest priority group, then it's going to be named as a substituent, and it's going to be given the name oxo. So as we have mentioned, we have the common names. For example, acetaldehyde, benzaldehyde. By the way, the common names of the aldehyde comes from the acids. You look for the acid that the aldehyde can be prepared from, and you remove the IC and you add the word aldehyde. For example, acetic acid, then it's acetaldehyde. Benzoic acid, it's benzaldehyde, and so on. The EUPAC name, as we have mentioned, you have the alkane, you remove the E, and then you add the al group. If it's not the highest priority functional group, it's going to be named as a 4-myl group. In case of ketones, as we said, you can name the different alkyl groups, and then you add the word ketone, or you have the common names well known such as acetone and acetophenone. If it's not the highest priority functional group, then you're going to name it as an oxo group. This is the order of priorities. You have the carboxylic, the aldehydic, the carbonyl, you have the unsaturated compounds. By the way, the alcohol comes before the unsaturated compounds, and so on. Now, if we discuss the methods of synthesis of these compounds, we can prepare them from so many different starting materials. You can prepare them by oxidation, you can prepare them by reduction, you can prepare them by from unsaturated compounds, and you can prepare them from alkyl halides. Let's look at the oxidation method. So the carbonyl compounds of aldehydes and ketones can be prepared by oxidation of alcohols. If we use a primary alcohol to get an aldehyde, a non-specific oxidizing agent will not stop at the aldehyde and will give the carboxylic acid. However, if we use something like PCC, it's a selective oxidizing agent, it will stop at the aldehyde. In case of secondary alcohols, if you oxidize them, even if you use a non-selective oxidizing agent, you will end up with the ketone and you will not proceed further than that. However, we still have a selective oxidizing agent, which is the open-hour oxidation, where you take the secondary alcohol and you add acetone in presence of aluminium tertiary butoxide, and you end up with the ketonic compound, and the acetone will be reduced into the alcohol. So actually, in other words, it's as if you are exchanging this group with this group. This is all what you're doing. Why do we need a specific oxidizing agent like open-hour if non-selective oxidation gives the ketone and stops at it? In case if you have an oxidizable group in the side chain and you fear it will be oxidized if you use a non-selective oxidizing agent. In this case, you can use the open-hour oxidation. The second method of preparation of aldehydes and ketones is from alkynes. When you hydrate them, they will give the first step exactly like alkenes, where they will introduce an OH on one carbon and a hydrogen on the other carbon based on whether you're using Markovnikov or anti-Markovnikov conditions. However, this is called an enol, en, which is the double bond, ol, which is the hydroxy group, and these exist in equilibrium with the ketonic compound or aldehydic compound. If we use an anti-Markovnikov hydration, you will end up with the hydrogen on the non-terminal carbon and the OH on the terminal carbon, and again you will have a tautomerism giving the aldehyde. So Markovnikov addition of water on an alkyne gives a ketonic compound, while anti-Markovnikov addition gives the aldehydic compound. So this is how you can prepare them from alkynes. The third method is from halogens. If you have two halogens attached to the same carbon, we call this a geminal dihalide. Please refer to the video of alkyl halides. This is a geminal dihalide. If you remove the halogens and you place a molecule of water in their place, either in acid medium or in alkaline medium, sorry, you can only use the alkaline medium. If you substitute these halogens by two OHs, a regular nucleophilic substitution reaction, what happens is that the geminal Ol is a unstable compound that breaks down giving an aldehyde or a ketone. It breaks down giving a carbonyl compound. So this is the third method. Finally, you can prepare them by reduction from acids and acid derivatives. From acids, you can reduce the acid derivatives such as the acid halides. You have a selective reducing agent which is the Rosenmund, where you use hydrogen, palladium, barium sulfate as a poison for the catalysts, sulfur and quinoline. The hydrogen and the palladium is a regular catalytic reducing agent, catalytic reduction. However, when you poison the catalyst using barium sulfate, sulfur and quinoline, you can stop at the aldehyde. You can also reduce esters using a selective oxidizing agent, which is the dibal at negative 80 degrees centigrade, and you again will end up with the aldehyde. So this is how you can prepare carbonyl compounds, which are the aldehydes from acid derivatives. You can prepare them from the acid halides using the Rosenmund reduction, giving the aldehyde, or the ester using the dibal, giving the aldehyde. However, if you need to prepare the ketone, you will have to use Grignard or organometallic agents. How do we do that? It's exactly the same way. You have the acid derivative, say the acid halide or the ester, doesn't make a big difference, and you add the Grignard reagent. You have a partial negative charge and a partial positive charge, and attack the double bond breaks, and then it reforms, giving away the group that was here, whether the halogen or the other alcohol or the alcohol part of the ester. This is your product. However, this product still contains a carbonyl, so it can react with another molecule of Grignard, giving the tertiary alcohol. So this is not a highly preferable method for the synthesis of ketones from acid derivatives by using Grignard. However, we have a selective reagent that reacts only with acid halides, which is the dialkyl cadmium. You can use any alkyl group and you attach it to the cadmium. Again, this alkyl group is carrying a partial negative charge, so it attacks the carbonyl, giving the ketone. Now your product is not able to react with your organometallic compound because dialkyl cadmiums are only selective to acid halides. They cannot react with any carbonyl compound. They only react with acid halides. This is how you can produce ketones in a selective way from acid derivatives. So as we've mentioned, you can prepare alcohols and you can prepare aldehydes and ketones through 4 different methods, either oxidation or reduction. These are 2 methods. Oxidation of alcohols or reduction of acids and their derivatives. These are 2 different methods. You can prepare them from geminal dihalides and you can prepare them from alkynes. In case of oxidation, you can oxidize primary alcohol, but you will not stop at the aldehyde. You will continue to the acid, except if you use a selective oxidizing agent such as PCC. In case of secondary alcohol, you will stop at the ketones, so you do not need a selective oxidizing agent, except if you have in the side chain an oxidizable group that you fear its oxidation. If you use a non-selective oxidizing agent, in this case you can use Oppenauer oxidation, where you add acetone and aluminium tertiary butoxide. In this case, these 2 functional groups are exchanged in each other's place, and you end up with the ketone and isopropanol as a byproduct. From alkynes, as we said, you can hydrate these compounds either in an anti-Markovnikov or in a Markovnikov manner, giving aldehydes in case of anti-Markovnikov and ketones in case of Markovnikov. Geminal dihalides can be, their halogens can be substituted by any hydroxyl group through a nucleophilic substitution reaction, giving the two hydroxyl groups. And these are non-unstable compounds. They lose a molecule of water, giving the carbonyl compounds. Finally, as we said, you can prepare them from acid derivatives through reduction. It's either a selective reduction of acid halides using the Rosamond reducing agent, stopping at the aldehyde, or you can use the Grignard and stop at the ketone. But as we mentioned, this is not a selective method, and it might proceed to the tertiary alcohol, and it's preferable if we use the dialkyl cadmium. The second method is from esters, where we can reduce them using the dibal. Dibal stands for diisobutyl aluminium hydride. We usually use this reaction at negative 78 degrees centigrade, and for facilitating we say negative 80 degrees centigrade. You end up with the aldehydic compound. If you need a ketone, you can again use Grignard to produce a ketone, but as we mentioned, this is not selective and it can proceed to the tertiary alcohol, so this is not a preferable method. Finally, for only aromatic ketones, you can use the Friedel-Crafts acylation, where you introduce an acyl group to the benzene ring, giving a ketonic compound. You can use the acid halides or the anhydrides. These are the only two acid derivatives that can be used to prepare ketonic compounds, aromatic ketonic compounds. Finally, in case of the physical characters of these compounds, these compounds do not have an oxygen attached to a hydrogen, so they cannot perform a hydrogen bond. However, they have an oxygen which is carrying a partial negative charge, so if they are placed in a container of water having a hydrogen having a partial positive charge, they can form a hydrogen bond with this hydrogen. So they cannot donate a hydrogen bond, they cannot form hydrogen bonds with each other. However, they can form hydrogen bond with molecules such as water. So we say that they are hydrogen bond acceptors. They can accept the hydrogen bond, but they cannot form it. They are incapable of forming hydrogen bond if they do not exist in the same medium with another molecule that has an OH in it. Accordingly, their melting and boiling points are regular. They are exactly the same as the alkane having the same number of carbons. However, their solubility is very much close to the solubility of alcohols because they can accept the hydrogen bond from water.